All right, so today I only have a few things for you. I don't know if we're going to finish early or not, but we'll go over a couple of things that will tie up a few things that we didn't study yet and linking to things that we have studied in this course, so I think you'll enjoy that. And I tried to get a way to validate the GTD solution, but I went through many references. I spent a lot of time in the last 2 days reading and going, with a fine-tooth comb through the calculations to make sure that we were doing them right and checking them against literature and things. And I've come to the conclusion that for sure we're doing it right. I tried to use full wave solvers to calculate. So what I'm talking about is this. Let me show you. I tried to use a full wave solver to calculate the field behind this disk. So I have a point source here. I have this PEC disk, and I wanted to calculate the field and compare it to a simulation of the field in the shadow, right, in the diffraction. So back behind this disk, the only component of the incident reflected and diffracted field is the diffracted field, right? So the total field behind the disk is diffracted only. And in the situation that I wanted to compare it to, we'll go over this in the class today though, but I wanted to look at the field at this point here, the field at that point, and try to find it also in full wave simulation. But I became convinced that the full wave solvers are not, either we're missing something, we're not modeling something here, or the full wave solver, one of the solvers I was trying to use, they have a array-based solver in CST called asymptotic solver that does a similar thing, geometrical optics, but and it includes diffraction, but it does diffraction using equivalent currents on the rim of the disk, which is PTD, right? So I don't know if it's an apple-to-apple comparison. I was unable to get a good comparison. All right. Okay. But first thing we're going to go over today is the curvature matrix of the transmitted wavefront. So we learned how to handle PEC conducting objects and how to calculate the reflected Q matrix given an incident field and its curvature matrix and the curvature matrix of a scattering object that was made out of PEC. We were able to use phase matching to find what the reflected Q matrix was. Once you have the reflected Q matrix, you can find the principal directions and the principal curvatures, thereby allowing you to calculate the divergence factor and to transport or propagate the electric field along the ray, right? Okay, but one major class of problems that we haven't solved yet is that of dielectric interfaces. What if the object itself is dielectric, right? And in that case, how do you calculate the transmitted Q matrix? So that's what we're going to do today, and it's very similar as what we did before. So now let's consider the case of a dielectric interface where an incident wavefront is both reflected and transmitted. So now we have an incident wavefront illuminating, say, a dielectric sphere in this case, but it could be any object. And the incident wavefront will reflect, so you get a reflected wavefront, and it will transmit. You'll get a transmitted wavefront as well, right? Okay, so we're going to do the exact same thing to find the Q matrix or formula to calculate the Q matrix of the transmitted wavefront. We're going to use phase matching. So, all right, we will derive the transmitted Q matrix of the transmitted wavefront using phase matching. First, we start with the phase function of the incident, the reflected, and the transmitted wavefronts at an arbitrary point in the incident, reflected, and transmitted pencils. All right? Okay, so now we have the addition of this factor K, K1 and K2. K represents the wave number in the respective medium. Here we have epsilon R1, here we have epsilon R2, all right? And K times S is what? Phase, very good. It's the actual phase, right? Okay, so the incident pencil is given by S incident, the phase at the point of, we can say the point of reflection and transmission here. The phase that the incident field carries up to that point, plus the phase along, or the distance along the axial ray, from that reference point, and plus the second order quadratic approximation of the incident wavefront, right? Okay, and we have the same thing now for oh, this should be reflected. For the reflected wavefront, the reflected pencil. And also now we have the transmitted phase function. So the transmitted phase function has K2 instead of K1, and it is given by the transmitted wavefront at the point of transmission, the z distance along the axial ray for the transmitted wavefront, and the second order quadratic approximation of the wavefront for the transmitted pencil, right? All right, good. So nothing new there, right? We just added now the transmitted pencil and the phase function for that, all right? Okay, now we can express these phase functions in the sigma coordinates. The sigma coordinates are the surface coordinates in the exact same way we did last time for the reflection from a PEC surface. So here we have, this formula is exactly the same as we had before when we did reflection from PEC surfaces. This formula is also exactly the same as before, except now we have the addition of K1, right? Because we have to distinguish between the two media. All right. Now, this one is calculated in the exact same way as the other two, except now we have Z transmitted dotted with the sigma 1, Z transmitted dotted with sigma 2 for the linear part, and then we have the projection matrices for the transmitted wavefront and the P33 for the transmitted wavefront. All right? Okay, now we perform phase matching. So what do we do for phase matching? K times S incident has to equal to K1 times S reflected. K1 times S incident has to equal to K1 times S reflected, has to equal to K2 times S transmitted. Okay, we've already done the phase matching procedure for this equality, right? And the incident and reflected phase function equalities. The result was Snell's law of reflection. We got that from matching linear terms. And an expression for the reflected Q matrix, which we obtain when we simply reflect the incident principal directions across the surface, thereby obtaining the reflected. These are not necessarily principal directions in the reflected wavefront, but two orthogonal directions in the reflected wavefront. We obtained this expression from matching the quadratic terms to calculate the reflected Q matrix. All right? Yeah? Okay. Now let's do the transmitted wavefront phase matching with the incident field wavefront. So we now match the incident and transmitted phase functions. Matching linear terms gives us the following. If we go back here, the linear terms are, for the transmitted wavefront are these, and the incident wavefront are these. We include the K1, all right, which is appearing over here. Oh my. Okay. So if you do that, so we have this for the incident is equal to this for the transmitted, and we can rewrite that as the sigma 1 coordinates has Z incident dotted with X1 sigma, Z incident dotted with X1 sigma for the X1 sigma. On the right-hand side of the equality, we have X1 sigma here, which is multiplying onto Z transmitted dotted with X1 sigma. So we get this equality from the X1 sigma coordinate, and we get this equality from the X2 sigma coordinate, all right? Okay. With these two formulas say that the projection of Z incident and Z transmitted into the tangent plane multiplied by the respective wave numbers are equal, because Z incident dotted with X1 sigma, which is in the tangent plane of the surface at the point of transmission, is equal to Z transmitted dotted with that same vector. So Z transmitted dotted with sigma 1 is the projection of Z transmitted into the tangent plane multiplied by K2 has to be equal to Z incident projected into the same tangent plane along the same axis multiplied by Z1, or K1 rather. So that is nothing but Snell's law of transmission, right? So Z transmitted dotted with Xn sigma here, where now n is equal to 1 or 2, is equal to sine theta transmitted divided by sine theta incident, by definition of the dot product there. And that's equal to K1 over K2. And you can write K1 as omega squared of mu1 epsilon 1 and K2 as omega squared of mu2 epsilon 2. And the omegas cancel and gives you this following familiar expression, Snell's law for transmission. So when we did phase matching for PEC reflective surfaces, or even in this case, we recover Snell's law of reflection, right? And when we do it for a dielectric interface and we match incident to transmitted wavefronts, the phase functions, then we get Snell's law of transmission from the linear terms. All right. So think of what you've learned before. Before you learned dielectric interface, half space, right? Epsilon 1 all the way to the left, epsilon 2 all the way to the right, right? And you probably knew it or you didn't, but when we derived the Fresnel transmission reflection coefficients and Snell's laws in that situation, you were doing phase matching, right? That's how you come up with all of these expressions. You do phase matching. What is different between that and what we're doing here? Okay, but still we have locally a plane wave along each ray, right? In geometrical optics. So we recover Snell's law of reflection and Snell's law of transmission when we match linear terms, right? Okay, and we have something additional in this situation. What is it? The curvatures, right? When you calculate these Snell's laws, you're always thinking of planar interfaces, right? So the interface is planar between two infinite dielectric media, half spaces, and therefore you only have these linear terms. And you do the exact same thing. So it should be familiar if you link it back to your undergraduate studies of electromagnetics. The only thing new here is that we have a curved wavefront, a curved surface, and a curved reflected wavefront, which is why we have these additional terms here. Look here. The phase function of a plane wave is only this, right? Along the ray, the phase changes only based on the k vector, right? And the distance along that, along which you have traveled from the reference point to the observation point, right? And if you do phase matching, Ks incident equal to Ks reflected or Ks incident equal to Ks transmitted with only the linear terms, you do exactly the same thing as you did in undergraduate electromagnetics. And you recover the same results because the interface is planar and the wavefronts are planar. Plane waves and planar interface, right? So this is a more general approach, but you're doing exactly the same thing, right? It's still phase matching. Okay. All right, so now we match the quadratic terms, which is a new thing, which is different than what we did in undergraduate theory or undergraduate studies of electromagnetics. Match the quadratic terms. So here's the quadratic term for the incident field. Here's the quadratic term for the transmitted field. And if you match them up with the respective K1s and K2s, then the following occurs. So here we can say that this whole thing is exactly the same as this whole thing, right? This whole thing is exactly the same as this. Or no, sorry. Yeah, that we want to keep, right? So what we can do then is keep the interior here, which is K1, P1 transmitted, Q incident, P1, or P incident rather, plus K1, P33 incident, Q sigma. That has to equal to K2, P transmitted transpose, Q transmitted times P transmitted, plus K2 times P33 transmitted Q sigma, all right? This has to hold for all of the coordinates. Okay.
Because of the interface x1i is equal to x1t, right?
At the interface,
That's how we
can. I think this is actually a typo now that I think about it. Let me go back. Because we should have expressed everything in terms of the coordinates of, yeah, let me just double check. Let's go back to when we did the same thing for the reflected wavefront. In the reflected wavefront, we re-expressed, yeah, that's what the problem is. So it's a typo, all right? Yeah, so let me go back. It should be all in terms of the surface coordinates, right? So here, this should be sigma as well. Sigma, 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 and sigma, right? So then these would also be sigma. These would also be sigma. And therefore, these drop out, this drops out, and this is equal to this with this and this, right? Which is what we have here. All right, very good. Good catch. Okay, now to solve this, we move this term to the left, and you'll see it appear here because they both multiply Q sigma. And then what do we have to do to solve this for Q transmitted? We need to multiply both sides of the equation with P transmitted inverse on the right. So you'll see P transmitted inverse on the right, P transmitted inverse on the right. And we need to multiply by P transmitted transpose inverse on the left. P transmitted transpose inverse to the left. And that's what's here, and that's what's here, right? And we isolate Q transmitted. So now we have the curvature matrix of the transmitted wavefront, which depends on the ratio of the wave numbers in the respective medium. It depends on the incident wavefront's Q matrix, and it depends on the curvature of the dielectric object, right? And the two wave numbers. Good. So now you can solve a very wide class of problems. You can solve dielectric lenses using geometrical optics. You can solve reflectors, dual reflector systems of parabolas and hyperboloids using geometrical optics and so forth, right? All you need is this transmitted Q matrix. Any questions? So how do we calculate the transmitted electric field and the reflected electric field? So now we can write an expression for the reflected and transmitted fields, right? Since we have derived equations for the reflected Q matrix and the transmitted Q matrix, we have the radii of curvatures for the reflected and transmitted wave fronts. Thus, we can compute the divergence factors, theoretically, right? The eigenvalues of these Q matrices. Okay? Or they're related to the eigenvalues. Since we know the fields at an arbitrary point sigma along the ray is given by some point, a known reference point, right? The electric field at a point 2 along a ray is given by the electric field at point 1 on a ray, multiplied by the divergence factor, multiplied by the phase factor e to the ik sigma. We can readily write the expressions for the transmitted and reflected fields in the following way. E reflected at Z reflected equal to sigma is equal to gamma times E incident evaluated on sigma, multiplied by e to the IKS reflected evaluated at sigma, multiplied by the divergence factor for the reflected pencil, right? And this gamma here is a dyadic or a tensor, however you want to label it. And it has tangential and normal components. And these are just the Fresnel reflection coefficients for a dielectric interface now, right? Remember, locally along a ray, it's a plane wave. That's what we got from the zeroth order solution. The m equal to 0 term of the Lunenburg-Klein expansion when we plugged it into the wave equation, right? So these are nothing but the plane wave Fresnel reflection and transmission coefficients, or reflection coefficients. And then for the transmitted field, we have T dotted with the incident. This should be a dot product, really, right? That's bad. There should be a dot product. So there are a couple typos today. And the T matrix is now the Fresnel reflection coefficients, or Fresnel transmission coefficients for a dielectric interface. Plane wave Fresnel reflection, plane wave Fresnel transmission coefficients for a dielectric interface, right? Okay, good. Very nice. Okay. The other thing I want to go through today is this diffraction problem here. So I tried to go through this in heavy detail, and I want to kind of walk you through the calculations so that you guys can apply the theory in the future if you have a problem involving diffraction. All right. So our problem, what's that?
I have a question with previous slide. What is
Sure.
the reference? The reference point will be at the surface.
The reference point is always the point O of transmission, reflection, or diffraction, right? You're talking about the reference point for this sigma, right? And this sigma. Yeah, this Z reflected equal to sigma with respect to the reference point, which is the point of transmission or reflection or diffraction. Okay, good. So let's get back to this. So here we have a point source illuminating a PEC disk. And the idea is that the incident field has a shadow boundary here. This is the incident shadow boundary. The reflected field has a shadow boundary here. This is the reflected shadow boundary. And anything back here is going to be purely due to diffraction. As a matter of fact, there's a very bright spot in the middle of the shadow, right? So if you shine a flashlight at a PEC disk, then you would expect a pure shadow behind it. But in fact, due to diffraction, there's a very bright spot in the middle of that shadow. All right? Okay, so the parameterization for the edge is that of a circle or a disk. And the derivative of the parameterization gives you the tangent vector, which is found to be phi hat. All right, so therefore, the edge tangent is phi hat, and that makes beta incident 90 degrees, where beta is the angle between the sigma incident vector and the edge tangent, right? And that's always 90 degrees in this case. All right, so we want to calculate the total field at Z equal to D2, and here's our formula for the diffracted field, right? All right, so step one is to compute the curvature of the diffracted wavefront. So R naught incident. The formula for the curvature of the diffracted wavefront is, let's jump ahead. It's this formula here. Oh, well, we derived it. This formula, all right? This one we derived from phase matching of an incident pencil. The incident pencil is phase function, and the curve now, a 2D curve instead of a two-dimensional surface, or 3D surface. Two-dimensional surface or a 1D curve. A space curve instead of a surface, right? And we derived this formula. Okay, so we need R naught incident. We know beta incident. We need the curvature of the edge, the space curve itself. We need sigma incident and sigma diffracted, and the normal to the curve that represents the edge. So R naught incident here is the radius of curvature of the incident wavefront at O in the plane through T and sigma I. So here's sigma I, for example. Here's sigma I. And T is orthogonal to that, right? Which makes the angle beta 90 degrees. And, okay, so in that plane, what is the radius of curvature of the incident wavefront? Well, the incident wavefront is spherical, so every point is umbilic, and therefore the radius of curvature is nothing but the distance from here to the point of diffraction, right? Which is D1 squared plus A squared square root of all that. Since the edge is the circumference of a circular disk, the edge curvature kappa is equal to 1 over A, right? Which is the radius of the disk. Intuitive. And the normal always points toward the center of rotation, right? And that normal is negative rho hat, which is given by this expression here. So far, so good, yeah? So sigma incident now is equal to R hat, because here's sigma incident, but if we start from the source, then we have sigma incident here with respect to Z, where the positive direction of Z is there. This would be theta incident, and then there's a phi incident, right? So R hat, sine theta incident, cosine phi incident, sine theta incident, sine phi incident, and cosine theta incident. And that's sigma incident, yeah? Since sigma incident is orthogonal to the edge tangent, we already concluded that beta incident is 90 degrees. Also, sigma diffracted is this vector, which if you write along the z-axis is like that, and it has its own spherical angles of the spherical angles that represent that position vector, right? Okay, so just like that. Now, theta diffracted is nothing but, so here's sigma diffracted, right? We can also write that here. This angle here is the same as this angle here, right? And that angle there, so this is also theta diffracted, that angle there is the inverse tangent of A divided by D2. Yeah? One last thing that we have to figure out is what phi diffracted is with respect to phi incident. So if we look at this thing on its side, then here is z and here is x. At this point, this is the top point here. The phi unit vector goes like that, which is equal to t hat. And the incident, sigma incident hat is like that. Sigma diffracted hat is like this. And therefore, if we translate these down into this plane here, we have sigma incident and sigma diffracted. And the difference in the angle phi here is 180 degrees, right? Is that right? Yeah. No, that's not right, right? Phi in the xz plane is always 0. So that's probably what mistake I was making. Okay, so I need to go back and check this, right? For some reason, I thought it was phi incident plus pi. As I was making these notes, last week really, I was solving these problems new. I was making these notes for this course. So yeah, we have, probably this is not correct, right? Maybe it's just phi diffracted is equal to phi incident. Okay. Yeah, that I agree with that. Phi diffracted is phi incident. Good. All right, so we can check that. So note, when beta incident equals to 90 degrees, the Keller cone opens up into a disk because here's the angle beta, which is equal to beta incident by the law of diffraction. And when beta is 90 degrees, that means you're coming normal onto the edge. Then you get a disk. It opens up into a disk, right? Good. All right. So we're going to have to go through this in real time then because there was an error here. But let's see. R naught incident is this. And that's for any omega I because it's umbilic. The curvature of the edge is 1 over A. And then sigma incident minus sigma diffracted is here, right? So we have sigma incident here, sigma incident here, sigma incident. And then we have sigma diffracted, sigma diffracted, sigma diffracted. Then we take the dot product with n, which is minus cosine phi minus sine phi incidence, right? Okay. Very good. Now, since we have cosine phi dotted with cosine phi here, we pick up a cosine phi squared. And then we have cosine phi diffracted and cosine phi incident. Yeah? All right, and so forth, right? But now this is not true. So this goes to 0. So this is not true. So now we have 1 over R1D. This is not the case anymore, right? So what we could probably write this as cosine of phi incident. So we end up with, and this one is sine of phi incident now. So that becomes a problem. We won't be able to simplify it in such a simple form now, okay? Because we don't pull out a minus sign. So now this is this minus that. And this is this minus that, right? So then this becomes, this just becomes minus, right? That's the only difference, yeah? Yeah, this is minus. So sine incident minus sine diffracted, because we can factor out this common cosine phi. And then here we have a minus sign here, right? Good. So things still are kind of nice, yeah? So this is a minus sign here. That's the only difference. Good. So this is a minus sign, yeah? All right. So let's see what we're saying here. What we're saying here is, here's the edge tangent at the top of the disk, right? Coming out of the board. Here's the normal. And here is sigma, which is the diffracted ray. And here's sigma incident, which is the incident ray. So is this clear, this drawing? Yeah? This represents the situation here at the top. All right. So if we subtract sigma incident minus sigma, then it should be a vector like this, which points opposite to the normal, right? So that dot product there, which we've taken care of here already, should result in, so this should be in the same plane as the normal, basically, right?
What is the meaning of sigma? Because
Sigma is sigma diffracted, yeah. Okay, so this is just a minus sign. That was the only difference that resulted from that. Okay. Good. All right. So maybe I will agree with full wave now. I'll have to check that. But I think that full wave solver is something's funny about it. Okay, so step 2, compute the curvature of the diffracted wavefront. Now that we have R1 diffracted, the radius of curvature of the diffracted wavefront, we can calculate the divergence factor, right? Except for this is now a minus sign here. And the next thing we need to compute the diffracted coordinate system unit vectors, all right? So normally you can use this formula explicitly if you would like, but let's see what this formula says so we can understand the rotation operator a little better. So here's the same situation. We have the tangent vector pointing out of the board at the top of the disk. We have sigma diffracted, sigma incident like that. And the first basis vector is sigma cross t crosses sigma. So let's take t and cross it with sigma, and we get this vector, which is orthogonal to the two, right? So this is t crosses sigma. And then we have to take sigma cross that. So sigma cross t crosses sigma brings us right back to t, right? If you work out these cross products. Okay, so sigma cross with t crosses sigma gives you your thumb out of the board, right? So that means this first vector here is in the same direction as t, which means it's alpha, yeah? Phi hat. So this is really phi hat, and that we call alpha. The polar vector, or the azimuthal vector is alpha. All right, then sigma cross, the other one is t cross the sigma. We know that one is orthogonal to phi hat and orthogonal to the diffracted ray, which means that this is beta or theta. All right, and t crosses sigma incident dotted with E naught incident allows us to account for, there's also this though, that accounts for the difference in the amplitude. All right, so we can calculate now, we can identify there that alpha equal to phi and beta equal to theta. All this rotation operator does is it rotates sigma incident to sigma, right? Because everything has to be orthogonal to the ray, the electric field. So sigma incident rotated, rotation operator applied to sigma incident rotates it to align with sigma, the diffracted ray. So all the other vectors rotate with it. Here's beta incident, right, which is orthogonal to sigma incident. But if you use the rotation operator to rotate the incident k vector to the diffracted k vector, then all this says is that the electric field on the diffracted ray has to be orthogonal to the ray. That's all that rotation operator does, all right? Okay, now let's compute the diffraction coefficients. So here's the way to compute the diffraction coefficients. If you use this form of it, which involves psi incident and psi reflected, then there's a systematic way to determine what those angles are. So here's the edge. Now we're looking at it on the side. The point of diffraction is point O. We have the incident vector here, like that, right? This is sigma incident. If we consider this as the top of the disk here, like that, this is the top, right? Then sigma incident is like that. Sigma reflected is here, right? And sigma diffracted is there. Okay, good. So let's calculate these psi angle, psi I and psi R. The magnitude of psi I and psi R are the angle between the diffracted ray and the incident ray. That's psi incident's magnitude without sign. And psi reflected is the angle between the diffracted ray and the reflected ray. All right? Okay. Don't worry about the sign yet. So how do we find these angles? Well, this angle is nothing but psi incident is nothing but alpha prime. So here, let's first find alpha double prime as our incident angle there, right? And alpha prime here is the angle from the top face to the diffracted array, or the incident array. That is equal to, if you draw a line like that, it's equal to pi over 2. This part gives you pi over 2, plus this angle, which is the same as this angle, right? This angle is the same as this angle. So it's pi over 2 plus alpha double prime. All right. So now, what is this angle then? This angle is nothing but this angle, right? And that angle is nothing but alpha prime minus theta prime. So it's alpha prime minus theta prime. But theta prime is easy to find. It's the inverse tangent of d2 over a, right? Okay. So that gives you psi I. Now psi r is, okay, so psi r. What is the angle psi r? The angle between psi or sigma incident and sigma reflected is what? So imagine this is, so look here. Imagine this is an infinite plane for now. The incident field is like that. The reflected field is like that. If you draw a line here, this angle is equal to this angle, right? By Snell's law of reflection. This angle here is this angle, right? No, it's this angle, I'm sorry. It's this angle here. But that angle is exactly the same as this angle. Okay, so that means that twice this angle, which is twice alpha double prime, is the angle between the incident and the reflected, right? The angle between the incident and reflected here is 2 alpha double prime. All right, now we just need to add psi I, because psi r is this angle, which is 2 alpha double prime plus psi I, which is here. Okay, the signs of these angles are equal to the sign of the shadow indicator in that, for the observation point for that array. So the observation point is here. That observation point has a shadow indicator for the incident field as +1, means it's in the shadow. And for the reflected field, also +1. So the sign of both these angles are positive. Now that you have psi I and psi r, you can calculate d soft and d hard this way. Okay? For the other edge, we get the exact same formulas. I just went through this to convince myself that you get the same results. So it should be symmetric, right? Okay. So then here is now how to calculate the diffracted field. We have everything we need to calculate the diffracted field. G of k and sigma is equal to this. We have the divergence factor is here. We have 1 over sine beta, but we know beta is 90 degrees. Theta hat, d soft, e theta incident, plus phi hat, d hard, e phi incident, yeah? Sigma now, point of diffraction to the observation point, is given by this. Sigma incident is given by that. Soft and hard diffraction coefficients in the radii of curvature we've calculated, except now we know that this is a minus sign. And E incident at the point of diffraction has the incident phase and amplitude. Okay, the incident field here, let me ask you a question. The incident field here, at this point, I want to calculate that, right? So I wrote it like this. Where is my divergence factor?
Sigma I.
Where? That's right. Because it's an umbilic wavefront, right? We know that the denominator is 1 over, so the determinant of Q incident, Q incident rather, is equal to the determinant. Let me write this out a little better. The determinant Q incident is equal to the determinant of 1 over R, or sigma we call it, right? 1 over sigma incident, 0, 0, because it's an umbilic wavefront, which is 1 over sigma I squared, right? But we know that the divergence factor is equal to the square root normally of the ratio of determinants, right? But in this case, the determinant of Q incident at sigma divided by the determinant of Q incident at sigma naught, but the reference point we're going to take is the origin. So this just becomes the determinant of Q incident at sigma, which is, or the square root of that, which is equal to 1 over sigma incidence, right? So that 1 over r is intuitive for us for a spherical wave, but now we can find the sort of the 1 over r, the field decay for any arbitrarily shaped wavefront, right? Using differential geometry. All right, so, and here's the problem where we're trying to find, we can't use this theory to find the field here because this is a caustic here, right? Think about this. If each of these rays has some kind of amplitude that adds up here, then what if I keep adding rays around the disk? Keep on adding more and more of them, right? You're just going to keep increasing this amplitude. And the wavefront here is converging, right? So the cross-sectional area of that wavefront of a ray tube is going to 0. So the divergence factor goes to infinity. So instead of looking right here on the axis, we can look here. Still, it's only a diffracted field that goes there. We can compare that with full wave simulation. So hopefully this minus sign fixes the problem. I'll figure it out. If I do, I'll upload or update the notes and upload them, all right? All right, so that's where we are with that problem, yeah? Okay, and we saw this last time, right? So one quick thing, I had to update the normal here. This is a new updated normal. Last class, I had a different way to calculate the normal. I don't think it was correct, but this is correct, right? So use this formula here for your normal if you need it, right? If you want to update your program. And then we went over this whole thing, right? So how to calculate the rays for this dual reflector program that we're doing in this course. All right, last thing I want to talk to you guys about in this entire class, all of semester, is the following. We learned method of moments, and we learned geometrical theory of diffraction, uniform asymptotic theory, and uniform theory of diffraction, and we learned geometrical optics. Now, there's a way to combine these two theories into a single theory, which allows us to solve a much wider class of problems. And this is a really cool thing. So it kind of connects two things that we learned in this semester. Ray-based techniques allow for the analysis of very electrically large scatterers, yet lacks mutual coupling between various parts of the scatter, i.e., ray-based techniques utilize localization principles, meaning that I break or I discretize the wavefront into small sections, and I allow a ray to carry each section of that wavefront to the scatterer, and I calculate the local reflection only from the wavefront that's locally around that ray, right? So it only knows about the scatterer locally where the point of reflection is. It doesn't know anything about the other parts of the scatter. Therefore, there's no mutual coupling between different parts of the scatter, right? The reflection only depends on the local properties and the local piece of the wavefront carried by that ray. All right. In contrast, the method of moments does account for full mutual coupling between all parts of the scatter, but cannot handle very large problems, right? So here we will attempt to combine the features of both approaches into an algorithm that can handle electrically large scatters and incorporate mutual coupling. Consider the problem depicted to the right, where we get this stuff from Stutzman's book, who is emeritus professor here at Virginia Tech. Consider the problem shown to the right. A source, J incident, radiates and produces an incident field. Applies an incident field to two scatterers. Here we have some material body, which is modeled using the method of moments here, and another scatterer here, which is not modeled using method of moments, all right? Okay, so whenever you use method of moments, you remove the material body and replace it by equivalent currents which are localized in free space, right? That's what we always have done when we did MoM method problems. And here we have a material structure which is not characterized by equivalent currents. So recall that the elements of the impedance matrix can be expressed in terms of the functional inner product between the nth test function and the electric field radiated by the nth basis function, right? In other words, ZMN of the impedance matrix is the functional inner product between the test function and the field radiated by the nth basis function. All right, well, that in integral form looks like this. So we take the dot product of the test function with the field radiated by the nth basis function and integrate over the domain of the test function. And that can be written compactly like this. The electric field due to the nth basis function reacted with the mth test source. All right? All right. In the method of moments, all material bodies are replaced by equivalent currents radiating in free space. We did that for the dielectric using volume equivalence principle, and we did it for the PEC objects using surface equivalence principles. Thus, the reaction of the mth test source with the field radiated by the nth basis function involves only the field which arrives via the direct shortest length free space path, as this is the only path possible. Say I have this, we represent this with basis functions and currents, then this might be the nth, let's say, basis function, and this is the mth testing function. The radiation that we consider is directly through the original body, right? It's the free space path, the direct path, because the objects are moved and we just have equivalent currents, right? All right. However, consider the situation where a structure is not represented by equivalent currents, like this material body here. In this case, the mth test source is reacted with not only the direct field, so let's do this again, mth, and here the nth. So the mth test source is reacted not only with the direct field due to the nth basis function, so this field, but also an additional field due to the presence of the scatterer not modeled by equivalent currents. So this nth basis function here also radiates to the, you know what, I should probably write it the other way because of the way this is. So here would be the nth, and then say here is the mth, and this radiates directly like that, but it also reflects off of some other object and goes here, right? So there are two fields arriving at the test function. That's radiated by equivalent currents that represent the structure which we're modeling with method of moments, and that which is indirect path, which is radiated by that same basis function, but interacts with some other object which is not modeled by equivalent currents and arrives at the mth test function. All right? Okay. So that means ZMN prime could be FM dotted with the now total field of AEN, the field arriving at the mth basis or test function directly along the free space path, plus BEN, which is the field arriving at the mth test function along a path through the scatterer not modeled by equivalent currents. Yes?
So is this kind of like the situation where you incorporate like coupling from the ground in like a antenna that's radiating, or like kind of like that?
No, it's a little different because here, the situation you're talking about, we actually model the ground plane using equivalent currents and method of moments, right? Here we might have, say, an impedance sheet, right? And we model the interaction between different parts of the impedance sheet with basis and test functions. And but let's say we have another scatterer over here that this impedance sheet we're designing in the presence of. Then the nth test or basis function radiates to the nth test source, plus it radiates and reflects off of that object and goes here. This object is not modeled with method of moments. There's no test functions or basis functions that we put on this other object. So it's like computing a numerical Green's function, which accounts for the presence of that object. All right? Okay, so we may set A equal to 1, right? So this could just be 1 in agreement with the original method of moment. And note that B here depends on M and N, right? So B, so let's say here's the nth and here's the mth. Well, if I change to this nth, then this will give you a different reflection. So this coefficient B depends on the M and N, right? All right. The idea is we can calculate BEN via other approaches, such as GTD or UAT and UTD, right? So that's super cool, right? We can account for these other parasitic scatterers in the environment that we're trying to design a metasurface in by using ray tracing techniques to account for the presence of that object and do the method of moment design on the impedance sheet. what that allows us to do is effectively create what's called a numerical Green's function, which approximates the true Green's function by incorporating the radiation due to the presence, right? Remember, Green's function is a
Oh, it's pretty covered.
no, Green's function is the solution to the wave equation for a delta function. Means I have a point source and I have to find the field radiated everywhere in the environment of which that point source is in. So now we're saying a point source is in the presence of this other scatterer. And I want to be able to calculate the electric field due to this source at any position of observation plus any position of the source to get a full Green's function, right? But here we're kind of numerically calculating it. It accounts for the environment. This is part of the environment. A Green's function represents the environment, radiation in the presence of the environment, right? So it's really cool. All right, so if we distribute this Fm onto these two terms, then we get FMEN, which is the regular impedance matrix for method of moments. And the other one is Fm into BEN, which is this new matrix, which is called ZEMG, which is an additional impedance matrix added to the usual MoM matrix, accounting for the additional scatter, which redirects energy toward the mth test function. Yeah? Okay, so we also have to do that to the voltage vector, right? So this incident field radiates directly here, carrying E incident, but also radiates here and reflects. And this is also another E incident. That's the same point, right? At the mth test source. So the same exact thing happens. We get another vector here, which is an additional voltage vector added to the usual method of moment voltage vector, accounting for the additional scatter, which redirects energy toward the mth test function, yeah? So now that we have these primed matrices, we can solve the primed matrix equation, and we can find the current on the body modeled using method of moments, operating in the presence of additional scatters not modeled by equivalent currents. How is this useful? Say I have a giant aircraft, right? So, oh my gosh, I'm not an artist here, right? All right, so say I want to design a metasurface for the nose cone. So this is a metasurface or an impedance sheath, right? But I need to design in the presence of this aircraft. So maybe I have some source here. Let's say source. That radiates here, but also you can use geometrical optics and GTD to find the true electric field due to the environment of the aircraft, right? Try designing a metasurface for this aircraft and having to use method of moments on the whole entire thing. That would be crazy. All right. Anyway, this is a really cool theory. And now you guys understand how to, and you can implement this. You can actually go and implement this approach. Another way to interpret the approach is that we're using GTD to find an approximate numerical Green's function for the method of moments problem, which accounts for radiation in the presence of the object not modeled by equivalent currents. One must ensure that the scatterer is not too close to the structure being modeled by method of moments, right? Because these are ray techniques. So you can't put the body that's not characterized by equivalent currents too close to your method of moments problem. All right? Yes?
You know how this would compare to something like the fast multipole method?
Fast multipole method is probably much more accurate, right? Fast multipole method, we're still doing full coupling on the whole structure. And yeah, that's a way to solve that big airplane problem, right? You could probably do that these days. But doing it iteratively is probably not going to happen if you want to do optimization, right? So still, if you want to design a nose cone metasurface for a giant aircraft, then you could use this technique and it will be fast enough to integrate into an optimization loop. Yeah? All right. That's it. You guys are all experts in electromagnetics, and I hope to see good research coming out of you at this university and in your career, all right, as an engineer. And I've appreciated having all of you in the course, and I would gladly work with any of you in the future. If you ever have problems, come to my office, and we can work things out. And I'm very confident in all of your capabilities now after 2 semesters of this book, these courses, and with me, all right? So yeah, thank you guys for being a part of this course.